everyone, in previous classes already we have studied about the quantum numbers, and by the help of quantum numbers we get an address of an electron. Means about the orbitals already we have studied there. In today's class I wish to discuss about the shapes of a orbital. Here first I wish to say once again the definition or the meaning of an orbitals here. So this is our nucleus and this is the space surrounded by this nucleus. When the probability of an electron is there, or in this region or in this space we got more chance to meet the electron. Here only the probability of an electron. So this space is called as an orbitals. Already we know that the orbitals are having a different sizes, different shapes and different orientations. In today's class I wish to discuss with you the shapes of orbitals. So see here, first I wish to discuss with you the shape of an s orbital. Shape of s orbital must be a spherical. Why? How we know the orbital is spherical? So see here, the probability of finding electron is equal in all directions. So consider this is a nucleus and around this nucleus we are having some space. In this a certain kind of space or a certain point of space we got some density. We got some density of an electron, means the probability of an electron. So the probability of an electron in a s orbital is equal in all direction. Then we know this direction is equal from this nucleus, means the s orbital is in a spherical shape. So by the electron density we now in this space we got the probability of an electron. So how the probability is there in this s orbital? So equal in all directions. So see here, it must be a spherical, since must be a spherical? S orbital. S orbital must be a spherical since the probability of finding electron is equal in all direction at a distance from a nucleus. At a particular distance or at a constant distance, there is a probability of an electron is there in some space. So that probability of an electron or that density is equal in all direction. Then what happened in a s orbital? We got or we know the shape of this s orbital is spherical. So see here, we are having x orientation and y orientation, but our s orbital is spherical in shape, because in all direction the density of an electron or the probability of an electron is equal. So consider this is our 1s orbital. What happened in a 2s orbital, and what is the structure of this 2s orbital? So the 2s orbital is also a spherical in shape, but what is the difference in 1s orbital and a 2s orbital? So see here, again this is our nucleus. We are having a x-axis and a y-axis there. In a 1s orbital we are having at a certain small distances, means near to the nucleus we find the density, but in 2s orbital we find the density little bit far from this nucleus. Here we find the density of an electron. So the 2s orbital is little bit bigger from this 1s orbital. So this is a little bit difference in 1s orbital and 2s orbital. Let me tell here about the shape of p orbital. Shape of p orbital. Here in this orbital we got the electron density in this shape, means in a dumbbelled shape. So here we got to meet the chance of an electron or the probability of an electron or the maximum probability of an electron in this shape in the p orbital we got here. So the shape of p orbital is dumbbell shape. So the shape of p orbital is dumbbell shape. So totally we are having a 3p orbitals, means px orbital, py orbital and pz orbital. Means the p orbitals are lie in x-axis and y-axis and z-axis. So see here, in a px orbital we are having, this is our x-axis and this is our y-axis and this is a z-axis. So in a px orbital we got this type of a structure. So this dumbbell shape p orbital lies on x orientation. And next one is, this is our y-axis and this is our x-axis and this is a z-axis. So in the py we got a dumbbell shaped lobe is lie on this y-axis. So here we got in the y orientation we got the maximum probability of an electron. And like this in a pz orbital, so this is our x-axis and y-axis and this is a z-axis. The dumbbell shape lies in a z orientation like this. So here we got the maximum probability of an electron in a z orientation. So this is all about the shape of p orbitals. We are having a 3p orbitals, px, py and pz. And next we are moving with a shape of d orbital. So this d orbital is double dumbbell in shape. Double dumbbell in a shape. Means in the d orbital we have the probability of an electron like this. So this is our electron density. Here we got the density in this shape. Here we got the density in this shape. So this is our d orbital. We are having totally in a 5 orientation of these double dumbbell shape d orbitals. So that those are dxy orbital and next dyz orbital and dzx orbital, dx square minus y square orbital and dz square orbital. So we are having a 5 types orientation orbitals here. So they are all double dumbbelled in a shape. It is very tough to visualize in a 3D manner, means in 3-dimensional manner. Just I wish to show in a 2-dimensional manner this double dumbbelled shape of these types of 5 types of an orbital. So see here, all you now, this is our x-axis and this is our y-axis and this is our z-axis. In a dxy orbital, the dumbbell is in between x orientation and a y orientation. So like this dxy orbital is there. And next one is x-axis, y-axis and z-axis. So this is a YZ. The dumbbell shape is present in between the Y and Z orientation. Y and Z orientation. So like this. So this is our YZ orbital. And next one is DZX. So same here. The dumbbell shape lies in between the Z and X axis here. Z and X axis. So this is our X axis, Y axis and a Z axis. So dzx is in between z and x-axis. So like this. So this is our dz x-axis. And next is dx square minus y square. Dx square minus y square. So see here. So this is our y-axis and this is our x-axis and this is our z-axis. So how we got here? Here the dumbbell shape is present on that x-axis only, above that axis. So like this we got the dumbbell shape in a x on the x-axis and on the y-axis. So like this. In a dz square orbital, this is our y-axis and this is our x-axis and this is our z-axis. So next, here I draw the dz square orbital. Here what happened? The double dumbbell shape lie on this type. So this is our one dumbbell shape and another is surrounded like this. So another one is surrounded like this. This is our dz square. So these are all 5 orbitals of d orbital. So these are the shape of d orbitals. So this is all about the shape of d orbitals. We are having a totally 5 d orbitals, means dxy orbital, dyz orbital, dzx orbital, dx square minus y square orbital and the dz square orbital. So these are 5 different types of orientations of the d orbitals is here. So I hope you got a clearance about the shape of orbitals like a s orbital, p orbital and the d orbital. I wish to repeat these orbitals here. We are having a spherical shape in a s orbital, dumbbell shape in a p orbitals and double dumbbell shape in a z orbitals. And another term is that is node. So what is the meaning of node and what is the meaning of a radial node, angular node? So see here, I already told you the total probability density is given to us the shapes of an orbital. So see here, in an example of a s orbital, we are having the density, the probability of density, means the probability of density is denoted by a psi square, probability of density. So this probability of density gives us the shape of an orbitals. So see here, in a s orbital, this is our nucleus. We have the probability density in this region. In certain space, we got the probability of density of an electron, means the density of wave function. So this probability density is equal in all direction in a s orbital. Then we know the shape of a s orbital is spherical in shape. I hope you got it. So once again I wish to say here, the shape of an orbital is given by this probability of density. So we got the probability of density in the s orbital is equal in all direction. Then we got to know the shape of s orbital is spherical in a shape. So like this, as we move away from the nucleus, so here I got the probability of density. So then as I move away from the nucleus in this region, so in this region I don't get any probability of a density. And next, in a 2s orbital, so see here, so this is our nucleus and this is a density I got for a 1s orbital. This is a density I got for a 1s orbital. And next, as I move away from the nucleus in this region, so see here, so in this region, in this empty region, I don't get any probability density here. I don't get any probability density. As I move away from the nucleus, means up to here I got again the probability of a density or the probability of electrons takes place in this region. So this region I mentioned as a 2s orbital. So this region I mentioned a 1s orbital. And next, as I move again away from the nucleus, means in this region, so here, so observe this empty region, here again I don't get any probability of a density. I don't get any kind of density of electron in this space. So this empty space is called as a node or a surface of a node. So see here, the reason where this probability density function reduces to a 0 is called nodal surfaces or simply nodes. So see here, this is the reason here the probability density function is reduces to 0. Here nothing is there. So this space is empty. We didn't get the probability density here. So this is called as a nodal surfaces or simply nodes. So for example, for 1s orbital, so see here, this is our 1s orbital, and near to this nucleus we got a 1s orbital probability density or to meet the chance of an electron here. So what happened? In a 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as we move away from it. As we move away from this nucleus, it becomes sharply to, or it reduces sharply to radius, and it becomes 0 here. And next on the other hand, for a 2s orbital, so this is our 2s orbital. This is our 2s orbital. What happened in a 2s orbital? The probability density first decreases sharply to 0. The probability density, so see here, for the 2s orbital, here first we don't have any electron density. So first it decreases the probability density sharply to 0, and as we move away from the nucleus, then we got some density. It increases the probability density and again it decreases the probability density. So see here, in a 2s orbital, the probability density first decreases sharply to 0 and again start increasing after reaching a small maxima. It decreases again and approach to a 0. So see here, this is a nucleus. First, for the 2s orbital, first we don't have any electron density. So first it decreases to 0 and at a certain point increases a probability density, and when we reach a certain point or a maximum point, then again it decreases the probability density and it get to a 0. So to this 2s orbital. Just see, observe these graphs. These graphs also shows about this nodals. These graphs are plots versus the variation of this probability density. I already told you the probability density. See here, the probability density is nothing but a wave function, square of wave function. So the probability density as a function distance is of an r. So this is the distance, it is denoted by the r. In a 1s orbital, the probability density is maximum. In a 1s orbital, the probability density is maximum. As we go away from the nucleus, means r is increases, then what happened? It becomes 0. And in a 1s orbital, what happened? First decreases the probability density, and at a certain point again it increases, and again at a certain point again it goes to decreases. So see here also we are having a empty space for the 2s orbital, and here also we are having an empty space for the 2s orbital. Here also the probability density becomes 0, and here also the probability density becomes 0 for the 2s orbital. So first we decreases the probability density and we reach that probability density. Again at a certain point, again it going to decreases as we are away from the radius. So see here, as we are away from the radius, so here again it decreases. And see here, we are having two types of nodes. One is radial nodes and another one is angular nodes. So these are our radial nodes. In a s orbital we are having a radial nodes. These are called as radial nodes. And in a p orbital, this is our x-axis, y-axis, we are having a dumbbell shape p orbital. So in this dumbbell shape p orbital or in this double dumbbell shape d orbitals, we are having in certain angles, we are having here also we are having a nodes. So the nodes present in these type of orbitals called as angular nodes. Angular nodes. So for the atom of a principal quantum number, we have to calculate the number of nodes here. So what is the formula to calculate the number of nodes? So see here, the number of nodes in a radial nodes, or the formula for radial nodes. What's n minus L minus 1. So this is the formula to calculate radial nodes. And next for angular nodes. For angular nodes, we are having the formula L only. And for total nodes, see here, radial nodes plus angular nodes means n minus L minus 1 plus L. So minus L plus L cancel, then what will be the answer comes? N minus 1. So this is the formula for total number of nodes. So this is all about the nodes and shape of the orbital. Here n is the principal quantum number. I hope you got very clearance about this topic, about the shape of orbital and the nodes, radial nodes, angular nodes, and formula for that radial nodes, angular nodes, and the total nodes. In a next class, I will come with energies of orbitals. How the orbitals are different in their energies. How the electrons filled according to their energies in that orbitals. So I wish to complete this class here only. Thank you.